Hey, Ganlon, welcome. Still in time, we haven't started yet. Um, but I think we should do so now. Where's the queue? Yeah, I'll switch my audio. Won't be able to hear you for a second there, but be right back.
By the way, can anyone hear my mouse and my keyboard? Because
Okay.
I think
We're live.
I can't. We are live already.
We are live now.
You should come on. You should have given us a few seconds of warning.
Sorry.
Oh, hey, we're
I
live.
clicked the wrong button.
Hey, everyone, we're
like
live. What if we were here? I don't know, doing something inconvenient, and you just tell us, "Oh, you're live. Everyone is listening to you."
Yes.
Thank you.
Doing stupid stuff. That's why
so. I was at my doctor's. We're live. Oh, okay.
Yeah, come on. We need to get better organized here, Michael. This is not professional.
It's very professional.
No, it's not. I mean,
It's
anyway, guys, welcome to Distant Radio 3305. This is another episode of Dangerous Cosmology. Here we have me, Nightfall Zero, broadcasting live from the Red Comet. Then we have Commander, that Michael, who is, as usual, organizing the technical side of the broadcast. We are starting a bit late because, as usual, he was having some technical issues. Yep.
Always.
Yeah, always blame the technical
actually,
issues.
I was just slow, so...
I was trying to save you.
Yeah, I know I'm blonde like that.
I was trying to do you a favor. Anyway.
Thank you.
We also have Commander... No worries, you're welcome. We also have Commander Selfish Pie. I think it's the first time you're here, right? Listening to this segment.
Actually, it's the second time. I missed last week.
Good. I'm a terrible host because I don't even remember.
Yeah, I remember you.
Good.
Thank you.
Someone does. I act all proper, but I'm really not. And we also have Commander Ganlan, who has been silent since joining, so I'm not sure if his communication systems are actually working or if he is just lost in a black hole and trying to scream for help, but we can't hear him. Hello, Ganlan, are you here?
He's lost.
Yeah, he is lost. And of course we have our dear Dr. Commander Shoba. Welcome. Thank you again for taking time to be here for us.
No, thank you for having me. It's always fun.
Indeed. So,
Yes.
I hope that you guys are faring well in Elite. We are getting closer and closer to Colonia. Myself, I had the time to visit
I'm not.
quite... Well, because you're slow at everything. Okay, you said it yourself. You're okay. It's fine. But I am having fun myself. I had a chance to hop into a ship with Dr. Nagi, and he brought me quite close to a black hole. I was always kind of scared of getting close to a black hole, but since it wasn't my ship, I didn't really care much. And I managed to overcome my fears, and now I am a better pilot for it. So this trip is helping me overcome some of the most problematic fears of space I had. So it's all good. But here we are again. The topic for this week for Dangerous Cosmology is going to be quantum physics/mechanics. Whatever the difference is, it will actually be one of the questions to our doctor to explain the difference between those two terms, because we often hear those terms, quantum. Sometimes you hear quantum physics, sometimes quantum mechanics.
I also have to preface this week's evening by saying I'm a bit less qualified about this topic than the previous ones. I mean, I studied quantum mechanics, I taught it at master level, but I don't actually work with it that much anymore, only sometimes, and only specific parts of it.
Yeah, let's remind everyone who is listening that Shoba here is a professional cosmologist working at UCL, but last week the topic of quantum mechanics popped up, and since she mentioned that she taught quantum mechanics in the past, and maybe you still do sometimes, no?
No.
But she did, so she has the knowledge of it, and I believe that we have received some questions that she will be able to answer.
I'll do my best.
Yes, please do. You don't want to, we have our radio name on it. You need to be worthy of our channel, okay?
Absolutely.
Yes, indeed.
Yeah. So last time we talked about time, and as I mentioned in the advertisement we sent, we are moving away temporarily from the very big to the very small. We're going to talk about what happens when things get so small that, shit starts happening and no one really understands what's going on anymore. So, starts from the basics. Let's start from the basics. When we talk about the quantum, what do we actually intend?
Well, quantum mechanics is the study of what's very, very small. And it's called quantum mechanics because we realized very early on, more than 100 years ago, that some things at the size of particles are not continuous. They only have set values that they can have. Typically energy levels of light. So sometimes when you shine only a specific frequency of light on a material, only some very specific colors will bounce back. So that's kind of specific levels are the origin of the word quantum.
Okay. So you're saying that that everything is not smooth, but you can only have specific states, right?
Yeah. So yeah, that's the gist of it. So we realized very early on, like if you collide particles together, they can only go one way or the opposite and never in between. Or if you shine particles through a slit, they will only land in some exact positions and not others, and that kind of thing. Although not everything at the level of particles is quantum. Some things are continuous, like position, that is still fine. But particles can still have all the positions they want, even if they prefer some. Just some things like energy levels are separated.
Okay, so not all reality is quantized, only some parts of it.
Yep.
Okay. Well, I believe that most of us know a bit about quantum mechanics. We're all nerds. We received quite a few questions, and some of them are actually quite hard. They require prior knowledge, most likely, and they obviously come from people that studied this already. We will try to address them, but if things get too complicated, they may require hours upon hours of explanation to clarify them. If that is the case, I will advise the interested parties to just continue the conversation privately with Shoba, because we will
not
try
privately,
to give
but in the public chat so everyone can read it.
Yeah. I mean,
Please.
out of this segment, because we don't really have all night, sadly. But we are thinking if this goes well and there is plenty of interest, we may have additional shows next week still about quantum mechanics. We will see if there is a chance. So we will start with some of the questions we received. We can go in order, but I actually want to start with the elephant in the room.
Mm.
And that is quantum gravity.
Oh God! Straight away.
Yes.
All
right,
away
then.
from the topic.
You can tell it's a good question when you get a full-time scientist to groan.
Well, to be fair, it's really hard to find an easy question, because so far the ones that we have received on the interview questions channel, they're all quite involved.
No, that's good. That's good. I can provide background, I don't have to go super technical right away. Quantum gravity is fine.
Okay.
It's a strange place to start. So quantum gravity is trying to unify, quantum physics and gravity. as in general relativity.
Because if I remember correctly, quantum mechanics and physics kind of contradicts in some instances GR, right?
Yeah, things don't work out if you try to calculate things using your quantum field theory on a background that's not flat, of space-time that's not flat. Well, okay, we have to back up a few steps here.
I'll leave the microphone to you, and you choose what to talk about, okay?
I'll make it as short as I can. So, quantum mechanics, the thing people think about with Schrödinger scat, different states of particles,
we have a question for that.
Slits and so on.
We have a question for that.
I know. But that quantum mechanics people have in mind is only one of the building blocks of what is our best theory of very small things. So, which is quantum field theory. Quantum field theory is built on quantum mechanics plus field theory plus a few add-ons that have come over the years. And that theory is extremely successful at dealing with particle physics. All the LHC collisions, predicting the Higgs boson mass and all that stuff works super well on that side of things, the very small. And it also integrates special relativity, so the effect of slowing down of time when you go close to the speed of light, that's part of it too, that's fine. And then at the other end of the scale, you've got general relativity, which deals with space-time and how space-time bends because of matter, and how matter bends space-time and space-time makes matter move. So this kind of dual relationship between space-time and matter. And it turns out you really can't combine them. If you try to work out things, putting them together, all the answers you get are nonsense. Because basically, in quantum physics, quantum field theory, particles can appear and disappear out of existence really fast. So you always have in a vacuum particles popping in and out of existence, kind of like a background. But according to GR, those particles should bend space-time. They should have lots of gravitational bending energy, basically. So when you try to work out things like the energy that the vacuum contains using these two theories, you get completely different answers, which are both wrong. So that's a problem. They don't work together. They work very well for the things they were designed to do, but they're not unified. So we'd really like a theory of quantum gravity that can predict both things at the same time correctly. That's the state of theoretical physics, I think, nowadays is the biggest question everyone's trying to solve.
How likely it is to have a breakthrough, a major one, within our lifetime?
Quite likely. So you have to understand how physics theories work. So if you want to propose a new model of physics, there's kind of 3 steps you have to go through. First, you have to check that your new theory of physics predicts the things that we already know correctly, also correctly. So it cannot do worse than the things we already know. It
Makes
has to
sense.
get the 2 sides. Second, it has to predict something that the previous 2 things fail at. So show that it's better in some way, superseding it. In retrospect, it explains an extra thing. And then lastly, it has to make a prediction without knowing what will happen, and then test it and confirm it. So those are kind of the 3 steps of proving a theory in physics.
And I guess it needs to be tested and confirmed multiple times.
Even
just-
once can be quite dramatic. So when GR got its step 3, I mean, it was pretty dramatic. It said exactly how much the light of stars would bend during a solar eclipse, and it was exactly right. So that was pretty convincing to everyone.
Would
So
you
in terms
say,
of- Yeah.
would you say, as an example, like another example of step 3, in the case of GR, would you say the discovery of gravitational waves was also like a part of step 3?
No, that was already well established by then.
Ah, okay.
That's it didn't really need to be proven anymore. It did that already with atomic clocks. It did it with gravitational bending.
All
It
right.
has never failed at these big mass, big scale things. It has never failed. So it's kind of the opposite by now. Kind of depressing. You know that these 2 theories are not the whole truth, and yet in their domain they never fail. It's kind of frustrating in a way.
Well, they're just a missing link somewhere, I guess.
I guess. So in terms of this step 3 nowadays, there's a few theories that are on to step 3. So they've managed to explain both sides. Some of them managed to explain one extra thing, and they're now awaiting specific predictions to come true. So for example, there's supersymmetry. There's been awaiting results from the Large Hadron Collider for particles it predicted, and we haven't seen them yet, so it sits there, it's waiting. There's string theory, waiting for some things that could come along, like inflated cosmic strings and that kind of thing. So these theories are there. They are trying to prove themselves in a new thing. But they've been at that step for quite a long time, so hard to say. Will it work? They can't both be right, but they seem like our two best bets at the moment.
So we just have to wait, and something hopefully will happen, and we will have a major breakthrough that will change how we view the universe forever.
Well, if one of those two is correct, I mean, their predictions could be wrong too.
Yeah, no, of course. I'm trying to be optimistic here.
Yeah. I mean, string theory seems to have a lot of mainstream acceptance already.
I think it is it is the most well-known theory. I mean, you can hear it and read it everywhere. I know about supersymmetry, but I believe that it is less popular than string theory.
Yeah, probably. Well, they both have pros and cons. They're very different. But,
okay. Well, we will not go into string theory or supersymmetry, at least not today.
Oh, no, never.
Okay, never.
Get a theoretical physicist.
Yeah, I guess. Well, I guess.
Okay.
I can sell you one. I can force a theoretical physicist to come on this show.
I'm sure you have contacts, and I understand you can't be a master at everything.
Welcome, to say the least.
I'm sure I can bribe them with a beer.
Oh, they're cheap.
Oh yeah, we all are. You know what our salaries are? Terrible. Terrible is what our salaries are.
Cool. So you can buy a physicist for a beer. Keep that in mind in case you want some explanations. Just go to to the university, stand outside with a sign, free beer for explanations.
Hey, we have it organized now. It's called the Pint of Science here in the UK.
What?
Yeah. It's a science meetings in pubs. So you get scientists like in a pub, and then people come to talk to them, and then they all share pints.
Yeah, no, but are we talking about actual scientists, not just students?
No. Actual scientists. It's a big
like
event.
With degrees and all of that.
Yeah, it's a big event. The Pint of Science is a big thing in the UK.
I think this might be the only event that I would actually drink alcohol at, now that I'm hearing of this.
Well, sort of. Drinking with physicists is something else.
But if they all get drunk, will they still be able to explain string theory? Because
either a lot better or a lot worse,
Probably. Yeah, that's...
They might give you a really angry TLDR. It will never work!
Yeah. I guess then fights happen and scientists, getting into a fight drunk in a pub. It must be something to see at least once in a lifetime.
I've never
Anyway,
seen
it.
Thank you for clarifying that. It was just one of the questions, but I actually missed the fact that Michael himself submitted a few questions. He was
you
the
missed
first.
That
fact. Well, I missed them now. I was scrolling up and I forgot that
Okay,
I thought
no
that
problem.
I thought I was at the start of the list, but I was not because I'm a bad host.
Don't worry, just pick them at random.
My questions are better to cover later. Because of...
Okay.
Yeah, well, some of them are just for fun, actually. And some are
Well,
pretty serious.
As usual, our show is quite casual, as you can obviously hear. So it's more like a discussion than an interview. It's not really structured.
No, that's fine.
The people want to hear us talking about actual relevant stuff.
Well,
But,
your stuff is relevant.
yeah,
Anyway,
you decide on your
okay,
own what questions to take.
Well, we can decide all together. It's all right. Also,
Yeah, okay.
I would like to give Shoba a chance to organize what she wants to talk about because she's probably most qualified to to know how to outreach. But one of the things that is usually associated with quantum physics is the famous Schrodinger's cat. And
Schrodinger's cat.
Oh yes.
Exactly. And
Always a fun topic.
it is a bit cliche,
Very misunderstood.
very misunderstood, and we would like to share some light on this mysterious feline that is both alive and dead. You always hear about Schrodinger's cat in media whenever quantum physics is used as a trope or as a plot device, there is always some mention of Schrodinger's cat or something very similar to it. So what is this cat about?
So Schrodinger's cat was a thought experiment that Schrödinger came up with. Shortly after Einstein and his buddies formulated their first superposition of states theory. So they noticed that some things in the quantum world, like the spin of electrons, when you measure them, they come up either plus or minus, never anything in between. And if you don't measure them, if you just let your electrons sit there for a while, you have no way of telling what it will be when you eventually measure it. So it's kind of like it's both plus or minus until you actually measure it. So they formulated this in a mathematical way that says that it literally is both. So the state of the electron is both up and minus 50-50. So Schrödinger didn't like this. He thought it was a bit silly, and he didn't understand at the time where the limit was. So he kind of took it to an extreme of a cat in a box. So say that your cat you have a cat in a box, and its life depends on whether an electron is spin up or spin down. So you take your electron measuring machine, you connect it to a vial of poison or whatever, so that if it comes up plus, the poison will release and the cat will die, and if it comes up minus, the cat will live. So you set it up. You set it up to measure the result at some point in time, and you just wait outside the box, not knowing what's inside. So after a while, it's either been measured plus or minus. You don't know which. So inside the box, now the cat is either dead or alive, or is it both? Compared to you. And that was Schrödinger's argument, which was, in the context where he wrote it, it was a mistake. So he didn't like it. It was a way to make fun of the superposition of states. But obviously a cat, something as big as a cat, couldn't have two states at the same time. So it was not supposed to be taken as seriously as it was. And then as quantum mechanics developed, different people interpreted these equations in different ways. And said that the cat really was alive or dead, but most interpretations say that it's not. Something as big as a cat isn't quantum. Small things are quantum, but cats and people are not quantum. You are not a wave. You have a position.
So this Schrodinger's cat was actually something used to disprove, or to at least try to ridicule the idea of quantum.
But it was it was thinking about it. Where would the limit be? You know, he was trying to contribute to our
but the fact that nowadays this image of a cat in a box is used to actually, explain in a sense quantum mechanics, and again in many media you see it. When characters try to explain to each other, explain me quantum mechanics, they always bring up Schrödinger's cat.
Yeah, because
it's
easier to explain than say if you measure your electron, it will either be up or down, and you have no way of or not.
No. I'm saying just it's ironic that something that was originally created to disprove and to ridicule something is nowadays considered to be a useful tool to explain the validity of it.
It's a tool to explain it. It's not literally true. Okay,
I
all
believe
interpretations of quantum mechanics that are mainstream by now, most interpretations of quantum mechanics which are mainstream by now don't say that would literally happen. We've kind of moved past that.
I don't think anyone actually believes that cat is both. But yet, it is still used as a way to prove it, to prove the concept, to explain the concept at least.
Yeah, it should be clear it's an analogy. It's not literally how it works.
Yeah, I hope no one actually tried to do that.
Well, they did it with tiny animals.
Define tiny. Quantum ones?
Nearly quantum. I think the closest they got was a bit less than a micron big, bacteria or something. And they managed to freeze it. To freeze it to the point where its energy was low enough to be quantum, and that it interfered with itself a bit, so it behaved like a quantum system.
So what happened?
The whole thing.
What did it do?
Well, I mean, it behaved quantumly.
So,
in order to interfere with itself, it had to be both briefly. Yes. It was, it was tiny. It was not a cat. It was an ultra cold bacterium.
But if you shrink a cat a lot,
you can shrink things.
If you shrink
Well-
a cat a lot, then it will explode.
no, it is
Well,
my
no,
it
it will
is
form a cute cat horizon.
it is my axiom of the quantum cuteness. The smaller things get, the cuter they get. So
But
at one
quantum
point,
mechanics isn't cute.
at one point, because you can't really see it, it's in a box, but it is cute and not cute at the same time. That is that
Quantum
is the
cuteness.
thing. It's a quantum cuteness because that's how it works. I will write.
Yeah, with the same logic, you can explain any
I will write a
anything,
paper
yeah.
about it,
quantum
and
mechanics.
Please
you
do.
will,
I want to read it.
Yeah, and I'm sure it will be published with the highest honors. Anyway, let's move on to the next question, which I don't know, Michael. You sent some really weird ones.
Yes, I
What is
did.
your favorite proof that quantum is real?
No, I like that other one. I can do that one later. But
Okay, you don't like this one. You like the other one.
I'm
Okay.
seeing the list of questions. The first one is a good follow-up. Where is the border between quantum and not quantum? That's a very good question. It follows exactly from Schrödinger's cat.
Yeah, I knew it was good. It was going to be the next.
Yeah, but it follows.
Yeah,
You know.
go ahead. It's fine.
I think a
So-
lot about questions before I tell them.
Yeah, they're good questions.
Sorry,
I haven't seen all of them. The border between quantum and not quantum. I hear a dog.
Yeah.
Is
I
that
think we
normal?
were talking about cats for too long.
I think it's coming from Ganlan.
But
Don't lose your focus.
Yes, sorry,
Turn-
I'm hearing a dog barking in the background from one of you.
Yeah, it
It's
must be
fine.
selfish pie.
I don't have. Oh wait, no, I do have two dogs. What am I on about? They're not barking though.
No, it's mine. My damn dogs are barking at absolutely nothing.
Do you have a
because-
dog in your ship?
Yeah, of course. Where else? Outside it?
Well, of course. They're barking at the neutron stars because,
Yeah.
you know, they have to
Yeah,
protect me
neutron
from
stars.
that danger.
All right. Anyway,
Right, back on topic.
Yes, sorry.
Quantum and not quantum things. Cats, not quantum. Very small and cold bacteria, kind of quantum. Electrons, 100% quantum all the time. So what's the border between all these things? And what decides when a system stops behaving in a quantum way and starts behaving normally? And by normally, I mean the scales that we're used to in our everyday lives. It's been a very studied topic by a lot of people. It turns out it's very easy to break quantumness of a system. So one of the famous experiments they had was Hardy's paradox. Not Hardy's paradox, the measurement one. What was it called? The quantum eraser.
we
Experiment?
got questions for both of those things.
The delayed choice
We have-
experiment, do you mean that?
They're called different things. That sounds like it. Well, the point of the experiment
Quantum
is you
eraser and
send
delayed
the,
choice experiments are they develop one evolved from the other.
yeah, they're all versions of the double slit experiment.
Yeah.
But the idea is you send an electron firing just in between two slits in a screen. So you have a piece of cardboard, say, with two gaps in it, and you send an electron, you fire it in between the two slits. If you don't touch anything and you look at where the electron lands on a second piece of cardboard behind the first, it will always land in some specific places. So there's some places it will always miss, and there are some places it will always prefer. And you will get this pattern where it lands in some stripes and it doesn't land in some other stripes. So it's behaving quantumly. But if you think to yourself, well, it's still going through one of the two slits, it's still a particle, it can't go through literally both. So let's try to find out which slit it's going through. And you put a tiny detector, like a polarization detector, to measure one of its properties if it goes through the slit on the right, say. So, and then you try to run the experiment again, you will find it's not behaving quantumly anymore at all. Now it's just going straight through one slit or the other like a ball. It's not behaving in the strange quantum way where some places are preferred and some are not.
So it
It's
will
just
no
landing
longer
between the
miss
two.
some of the spots.
It will land exactly behind the slits. So kind of if you're shining a light through it, like if it's made of tiny balls that go straight.
Okay.
So it doesn't behave in the quantum way anymore. So putting a detector like that on one of the slits has ruined your experiment. It has stopped it behaving quantumly.
Sorry, you said light, but light behaves like a wave, right? Which is what?
Yeah, but if you think of shining a flashlight through two big slits, it will land behind the two slits like a shadow, like a projection.
Okay.
I'm not talking about tiny light effects.
Okay.
It's like quite a big thing. Right, so that breaks the quantum behavior.
So it's not really a matter of size.
It's not only a matter of size. It's a matter of size, energy, and time, actually. And as we've come to understand recently, I think there's been this quite a big shift in the last decades of our interpretation of this behavior. It's all down to something called quantum decoherence. And quantum decoherence it's basically measuring how not quantum your system is, how much it stops behaving as a superposition of states and it behaves like something normal. And what it comes down to is the more things the particle interacts with, the more it has to be in tune with its environment, the less it can behave as a pure superposition of two states. So when you're putting your electron through one of the detectors in the two slits, it's interacting with a lot of things in there and it's gaining extra information. For everything that the electron interacts with, it gains a trace of the things it interacted with, like a quantum entanglement in a way, which I'm sure we'll talk about later. It becomes sort of entangled to all the things it interacts with.
It gets dirty in a sense.
It gets dirty, exactly.
Okay.
It gets dirty from all the outside world it touches. And the more dirty it gets, the more it struggles to interact with the other version of itself that went through the other slit.
Because his friends don't like him anymore.
Yeah,
he's dirty.
Exactly.
Yeah, okay.
So one electron is kind of pure. It went through one side, one part of the wave function. The other part of it went through the detector and it became sort of polluted. So they don't recombine behind the screen anymore. That's the modern interpretation of it. And it's the same with microbes and cats and the light and everything. The more things interact with each other, the less quantum they become. So the cat in the box would actually be able to observe itself. It's not in a superposition of things. The molecules it's made of will touch each other, and it will decohere that way, even if no one sees it.
And of course, there is no way to measure something without interfering with it at all, because at least light has to interfere with it.
Yeah, you have to be very careful how you modify it by interaction. But it works super well, so that's nice. We've actually used all of this in technology and stuff.
So the answer is not exactly straightforward. You can't say just below this dimension it's quantum, because there's a lot of variables.
Right? To some extent you can. Photons are pretty simple, but everything after that
on
too.
Different factors like temperature and stuff like that too. Not only size is the thing.
Types of interaction is how do the world, yeah.
Okay.
So for example, if it recombines very quickly, if you send an electron down two paths at the same time and you recombine it quickly, it doesn't interact with anything. That works. If you send it through very, very long things like LIGO does, LIGO sends lasers through very, very, very long chambers. It sends photons down these very, very long tubes and bounces them back. And when they come back, they're still in phase. They're still able to do this quantum thing. But they have to keep the tubes empty of air and all of that stuff. There has to be a vacuum. Because the more things they interact with, the more dirty they get. And they wouldn't behave like this anymore. Plus you'd lose them in the case of LIGO.
Yeah,
That get
Kirov
absorbed.
on Twitch is asking, so Schrödinger's cat is a lie. Is being asked on Twitch.
Yeah, I don't think any physicists still think it's a real thing. I'm not sure how many ever believed it was a real thing. There were and still are, I'm sure, some fringes interpretations of quantum mechanics, or it's literally both, and what you see depends on the observer and consciousness and a whole bunch of crap. But probably not.
Well, I don't want to go too deep into this because it will just go on forever. But could one tie this to a theory of multiverse, where the cat is both, once you establish which one, you have both cats
Absolutely.
the universe
Yeah.
splits, and you have both cats just in different timelines.
Yeah, that is a very popular interpretation. It's called the many worlds interpretation. Because basically, even when one of your particles get dirty, you can't know which way it gets dirty. So when you observe your electron, it has to come up, spin up, or spin down, right? Plus or minus. So you know that because you interact with it, you're gonna, contaminate it, and it has to pick. It can't stay quantum. But that's not to say which one you would actually see. In many worlds, both happen, but you only get to see one.
That actually reminds me of a paradox I heard on a. I heard you mention consciousness, and it reminded me of this paradox called the quantum suicide paradox. Essentially, what it is that if you were to play Russian roulette with yourself, the way it works, or well, I'm gonna try again because there's sort of a story behind it. The story goes that there's this guy playing Russian roulette with himself.
That's retarded, but okay.
Yeah, and he pulls the trigger, and he pulls the trigger. Nothing happens. Does it again, nothing happens. And he can keep going for infinity because of this quote unquote quantum paradox, because of the fact that if he was to percept himself pulling the trigger, then the universe in which he died cannot technically exist because he wouldn't have been able to perceive himself. And so he just keeps on going and going because of that multiple universe thing.
Yeah, I've heard of that. It's a philosophical question more than physics. It's what happens if basically you say that death is impossible because there's a chance he might have missed when he pulled the trigger. The other version of him, the one that died, doesn't actually die, but his consciousness jumps to the timeline when they didn't die.
Mm-hmm.
There's no evidence that would happen.
I think they made a series of games about that.
I mean, it's pretty cool.
It would be
but,
hard to get evidence of that sort.
Well, you might have seen it by now. We see other people die, and the universe doesn't disappear. So why would your consciousness jump timeline? There's no process by which your consciousness can jump.
Do they die, or they are born in another universe?
Well, no, they were still there before.
I was trying to.
They just unplugged from the Matrix, dude.
Yeah, or something like that. And you can't prove that. You can't disprove that.
Yeah, sure, but yeah, there's no process that we know of for consciousness to jump between timelines. That's a bit of a stretch.
Yeah, no one's really tested it, but I think I'm hoping to go to Mars. But if I was to test it, I would do it when I'm like on my deathbed. It would be the way I want to go, just doing it for fun, because
Yeah, just let us know how it goes. Maybe film it as well.
Yeah.
Yeah,
also,
like introduce.
If that was the case, we would know by now, right?
Catalyst.
But we'd know by now, because people have died for like brief moments and then they're brought back. If that was true, then while they're dead, they would be in a different timeline where they missed their shot. But they don't report that. They come back and they don't remember.
Zone of transition.
What? No, that's not physics anymore.
Because they also lose their memory. They get amnesia.
I mean, that's
there has to be
like bad sci-fi by then.
Anyway, we are digressing.
I apologize.
Let's get back on topic.
No, don't apologize. It's all.
It's a
all
thing.
Fun. It's all right.
I'd heard it before.
We need to keep this light.
Yeah, it means that there's always a version of people in somewhere else that haven't died yet. Because when it comes to it, your death is always the result of one path.
Yeah, but at that point,
another.
it's not you anymore, so you don't really care.
Also, it doesn't really make sense. By that logic, there's a universe where Charlemagne hasn't died yet. And he's just like 1,000 years old. Because you can never die. I mean, its probabilities, but it becomes kind of nonsense if you take it to an extreme.
Yeah.
Yeah.
But it's fun to think about it.
Well, our bodies are not quantum, so we can die. That's the thing. Consciousness might
Death is the ultimate type of decoherence. For sure.
Yeah.
I want that written on my tombstone.
Decohered.
I have been decoherentized, or something like that.
Marco has decohered from this universe.
Exactly. Anyway, still from Michael, you had a list of questions here.
Yeah.
if Shoba, if you see anything that piques your interest, feel free to choose the next one. Otherwise, Michael, you were asking what is this? What is the one electron universe?
The one, the what?
I
Didn't
don't
you
know.
hear about
Michael
the
is
one
saying-
electron universe? It's a theory.
Oh, it's Feynman's thing.
It's
Feynman's
yeah, that
time
thing
looping
with-
theory. Yeah, I remember
exactly
that.
where the one electron is just bouncing back in time, back and forth in time, and crossing our plane of time.
I always thought
everywhere
just
at
kind
once.
of yeah, and then positrons that
Because-
was the same going backwards in time. I remember that. Yeah.
Yeah, because
it's
electrons just have every electron is exactly the same, or rather, it has exactly the same properties. Just to explain for the others who don't know what we're talking
Yeah, so
about.
basically, when you go from quantum mechanics to particle physics, you want to understand what particles are and how they, how particles can decay into each other, how they interact with each other. We end up with particle physics, where everything is not particles; it's really fields. And the thing that we see, like electrons, are just sitting on the field. They're a property of the field that kind of travels along space, because the field is everywhere. So there's an electron field. And on that electron field, there's like tiny specks, which are all the places where there is actually an electron. That's the vision of quantum field theory and particle physics. And it turns out in that model, all electrons are exactly identical. They have no names. They don't have any particle other than their mass and their place of existence, or at least their rough place of existence. They're not like a point. They have a distribution of places. So Feynman came up with this cool idea that actually all electrons are just the same, because someone asked them how come they're all like exactly identical. Why would there be absolute? How likely is it they will be all be exactly the same?
So by the same, you mean it's one electron?
Yeah, so that was his theory / joke, because I'm not sure if he was joking or not. He might have been. It's Feynman we're
Well,
talking about.
I'm hoping he was
jokes a lot,
joking
but
because
You're joking, Mr. Feynman. That's the title of his book.
yeah,
I'm hoping he was joking because this has just blown my mind because of the thing I do chemistry at my school and we've essentially just had the Pauli exclusion principle drilled into our brains, and so this is just ripping that to shreds if it's all the one electron.
What, the Pauli exclusion principle? That's still fine. It's just that it goes to the same place every time. So Feynman said it's one electron. When he gets to the end of time, he comes back traveling backwards through time with the opposite charge as a positron, which is the converse of an electron. So all the positrons we see are when it goes back to the beginning of time, then it starts again as another electron.
But it is also everywhere.
Well, no, it's
Because-
not. It's not everywhere at once. The field is where it has to travel on. The field is like the surface it lives on.
No, but if there is only one electron, okay, how can I have a banana, which is made of there are many electrons in a banana?
Yeah,
Okay?
so each of them is one time it went forward in time, and then it's come back a billion times to make up all the electrons.
yeah,
in that
but
banana.
so they form the shape of a banana because it's always a different point
Yeah.
that they end up for.
Yeah, they have to,
So-
because they still, when they go forward in time, they still feel the interactions of all the other electrons as normal. It's just they all started at the
So
beginning.
there's more than one electron.
No, it's the same one. It just goes backwards in time.
So why do you say the
Right.
other electrons?
It's it from the past. Come on.
So this is just a loop of the one electron, but in each loop there's a slight difference that allows it to appear as a separate electron.
No, that doesn't
Appear
make
as a
sense.
separate electron.
It follows
No.
all the paths at the same time.
No, the banana is there in the present. It's not like some parts of it are in the past.
No, but
Well,
all
we
these
only travel
electrons in
through
the
time in one
banana-
direction. The
Don't
electron
conf-
is supposedly
Yeah,
meant
exactly.
to travel through all of
Well,
time.
it
in an
travels
infinite
through
loop.
time in both. Yeah.
Sorry, say again.
So the electron travels in time through both directions. So it looks like many electrons to you. It's actually the same one going backwards and then forwards in front of your eyes many times.
yeah, with infinite speed.
No, not really. Well, it starts at the beginning of time. It goes at normal speed. It lives at normal speed. But at
yeah,
the
okay,
end of
not
time,
speed
it loops.
in the way we talk about it.
So you're saying that some parts of the banana are older than other parts, even if the banana was technically, it grew at the same time.
It's just a wild speculation. It's that at the beginning of time, all the electrons that existed were really the same electron. It would just come back to that point a billion
Did
times.
Feynman think of bananas?
I'm sure he did. He thought of everything. Feynman was a god.
That's reminding me of something that's. I'm always reminded of stuff, by the way. That's reminded me of something. I can't. It's really annoying me because I can't remember the name of it, but there was this movie that I was told about where this guy. He goes back in time to save his wife or girlfriend or whatever. And no matter what he does, she has to keep dying, and then eventually she gives him a necklace, right, when she's really old, because somehow he kept her alive, but she dies anyway of old age. So she gives him this necklace, and then he gives it to her in the past, therefore meaning that it's in a constant loop. And it was I remember an analysis of the movie that said that there was a technical name for something that exists in a time loop because it doesn't have an origin, but then how could it be in the time loop? There was a technical name for that.
Yeah, it's nonsense, unfortunately. So you can
right, cool.
Well, time travel is a different topic.
We should have asked
There's many
last week.
types of time travel. That particular model of time travel is a bit nonsense because of one question. If she gives the medallion to herself as a kid, how old are the atoms in that medallion? There's no answer, it's infinite. If time is only repeating and it's already written before, and you go in a loop back to when you were a kid and you give yourself an item, who made the item? No one. It only came from yourself. So you've broken causality. And if someone...
And that's a bad thing to do. Don't do that.
We'd know by now. Also, it wouldn't have an age. Atoms have to be made.
So what if he took a banana back to her?
The banana would be infinitely old and disgusting.
That explains the electrons!
Anyway, that was just a brief parenthesis into time. But if we want to make a segment only about time travel, we will think about it. If you are experienced enough about time travel.
I should have been here last
models
week.
of time travel in sci-fi.
All the various models and decide which one is. Well, we'll see. But we'll think about that. In the meantime, it's still about quantum today. So
yes.
There is Ashnak is asking about quantum superpositions. I know that you mentioned those previously when you were introducing things, but he's adding if there is a chance for you to expand a bit about the quantum superpositions we see in particle mixing, like an example in your case as a cosmologist in neutrino mixing. I don't know what that is.
Neutrino mixing. That's a bad example.
I don't know, I'm just reading the question. He says, which explains the missing solar E negative neutrinos.
I actually know for a fact that we have a neutrino physicist on FleetCo. Because I chatted
him in here.
Okay, well, that's new to me. Okay.
Give him a call.
He actually works on this stuff. Neutrino mixing, particle mixing, superposition of states. Different things. So mixing of different states is something I do come across in my work every day, but not in the context of neutrinos. It's what happens when you try to predict basically the color of anything. So you have an atom, say it's carbon, you bombard it with some UV, and then the colors that it shines back towards you will depend on quantum processes, and you have to work out the superpositions of states going on inside the atom to know what the result would be. So in that sense, it's super useful. It's also all of electronics ever. So your phone, transistors that are as small as a nanometer, they're all quantum.
I use my phone. I don't really understand how it works, but
yeah, they actually use quantum tunneling, don't they? Don't they? No, not tunneling.
They're profoundly quantum things. If you want to make something on that scale and you want to know how it will behave when you pass a current through it, which is literally how screens work, you have to know exactly the distribution function of the electron, and that assumes quantum mechanic principles, like it's at multiple places at once. So you have to work it in to know how electronics behaves. There's no way around it. So Yeah.
In the context of this question.
In the context of this question, particle mixing is something that we see every day. It's extremely important and it's fundamental to technology too. Now, the other example that he mentioned, neutrino mixing, is a different thing. So neutrino mixing is when we try to catch neutrinos from the sun. And so neutrinos are very light particles that almost never interact with normal particles. You have to build huge detectors to find them, like I'm sure we discussed a few weeks ago.
Yeah, we did.
So you miss many of them. So you will realize that the ones you predict to come from the fusion inside of the sun, compared to how many hit the Earth in our detectors, even though it's so inefficient, we're still missing about 2/3 of them. So that was a problem. And so people theorized, well, there are 3 flavors of neutrinos, like there are 3 flavors of all the other particles. You may not know this, but all particles come in 3 flavors. The electron has 2 cousins that are the same as it, except fat.
It's like the Mass Effect ending.
Kind of, yeah.
Okay.
They all come in 3 flavors, and only one of them is good. So all particles that you know of have 3 flavors. And we said maybe the 3 flavors of neutrinos, actually maybe it changes between them randomly, and we can only find the ones that are the good ones. You can see my air quotes. We can only find the good ones. That's why we missed 2/3. It's a suspicious number. And then we tested it, and it was true. Because we built a detector, I think, on the other side of the Earth, like further away. And the time it took to go between those two, some neutrinos had flipped. So we know that some neutrinos had flipped. So we've seen neutrinos flip between these 3 versions of themselves, which is a big problem, actually, because other things like electrons never do. So the electrons your body is made of never change into their other 2 heavier, ugly cousins, the muon and the tau.
I'm sure that would be painful.
Yeah, you would die. I mean, it would be pretty bad.
Okay.
Well, muons are theorized to be able to catalyze cold fusion. So if you had two muons suddenly change in close atoms in your body, I don't think the pain of fusion would be bearable.
Yeah. So when it changes, for a start, it would gain mass, which it can't really do. You know, in a conservation of mass, suddenly your electron is fat. That would be pretty weird. But it seems like neutrinos are the only particle that can do this. So you start with purely good electron neutrinos, and after some time, they'll start oscillating to the other 2 heavier cousins, muon and tau. And that's actually a big problem for particle physics. It's one of these things that we're talking about the phases of proving a theory. That's a stage 2. That's something that particle physics really struggles with at the moment. So any theory that can do it cleanly will have an advantage. Because it's not predicted by particle physics. This should not happen. That's neutrino mixing.
But it does, which means the current standard model is faulty.
Yeah, but you only have to add a small add-on to it, and then it kind of works. It's not elegant anymore.
We'll wait for the DLC, I guess.
It's a DLC. You add a small DLC hotfix to it.
Yeah.
I hope I don't have to pay for that. I've already spent too much on the original.
In taxes, yeah, I guess.
I got the Higgs boson DLC, and that was
so expensive.
Wait for the next season.
Yeah.
How much was it? Wasn't the LHC what, 2 billion? Ugh.
Yeah, pretty much. The LHC was, I think 13 billion total until they found the Higgs.
I was well off.
Depends if it's pounds or.
It was a lot of content, though.
A lot of content. That's true.
Yeah. So, anyway,
well, it proved all of particle physics.
Exactly.
It was never wrong except for this one specific case.
The reviews on Steam are great for the DLC.
LHC, 10 out of 10.
10 out of 10. We'll collide again. Anyway, there is another question from Michael, but I'll leave it for later because I know it's a hard one.
We're getting new ones.
I know we're getting new ones. They will never stop, but I still have a backlog. But let's see.
What? We're getting new ones?
Yeah,
new ones.
Yeah.
We're
getting new
today
ones.
it's just a
They'll
bag of
give you
jokes.
cancer.
Yeah, well, bad pun day.
Yeah, it's fine. But puns can be so
every day
bad.
bad
that
pun day?
Yeah, for me too.
They can be both good and bad at the same time. That's all right. So, Shaggy Dog. No, Shaggy Dog.
Well, he prefers Shaggy, I think.
I don't know. I just read
Shaggy Dog?
Shaggy Dog. I don't know.
That
Anyway.
guy.
That guy. On the matter of electrons, he's asking if an electron has infinite speed and speed slows time, then time doesn't exist for the electron, and therefore neither does space.
No, electrons don't have infinite speed. Electrons travel at normal speeds. They can try to get to the speed of light.
I think he was referring to Feynman's idea.
Even in Feynman's idea, electrons still travel normally. It's just when they get to the end, they start traveling back, but they still travel at normal speeds through time and space. Basically, the number of electrons at the start is just how many times it's gone back. Like if you use a time machine and always go back to the same place, there's more and more of you, you know? That's basically Feynman's idea. It doesn't travel at infinite speed, it just goes back at normal speeds.
Okay. Then we have we have a question from Commander Basti Wonder. This is a bit odd because it mixes quantum physics to black holes, I guess. Because he's asking if you could explain the relation between quantum fluctuations and Hawking's radiation, if there is one.
They're basically... Yeah, it's basically what happens when you try to use both in context. With the caveat that as we started, I think the first question was quantum gravity, we don't have it. If you're trying to deal with what would happen to quantum fluctuations in the context of a black hole, you probably need a full theory of quantum gravity to be sure that you're predicting the right thing, because we know that they don't work nicely together usually. But you can still try. So the theory of quantum plus black hole physics has been reasonably successful, although it's never been tested. And Hawking's idea of Hawking radiation is one of the most popular predictions to come out of that. As we mentioned briefly before in particle physics, sometimes in a complete vacuum, particles can pop out of nothing as long as they disappear quickly enough and they return the energy to the environment. So you always have this kind of soup of tiny particle pairs appearing and recombining all the time. So when they do that, their distribution isn't exactly on top of each other. There's a small spacing between them. And oversimplifying Hawking's idea massively, if that happens very close to an event horizon, sometimes one of these particles might be just outside and the other one might be just inside. So the one that's outside could escape and the one inside would stay in. So overall, energy has left the black hole. The vacuum inside the black hole has lost energy and it's been radiated away in this particle that's managed to escape, which is basically Hawking radiation. There's a bit more to it.
I'm sure there is.
So that's the theory, at least. And if you accept that, actually, it has very far-ranging consequences of information content of black holes and that kind of stuff. Because over time, they will lose mass by this process very, very slowly from their event horizon. Once in a while, some small amount of energy will escape. And so after billions and trillions of years, they will evaporate. Yep.
Well, we have another question that the same commander asked earlier. Sorry, I'm picking them up. I'm going from the bottom now. It's a bit hard to keep track of all of them at the same time, try to keep following the same thread of discussion. But he's saying that you mentioned earlier that the particles that spontaneously appear and disappear in a vacuum should have a leftover gravitational energy. But what about it's the same energy that propels dark energy?
Yeah,
I'm not sure how this question is structured, but
no, that's already onto something. That's a good one too.
Like he says, like an anti-gravitation.
Well, yeah, it's a big hint. Dark energy is a big hint as to which one of these theories is correct. So, general relativity and particle physics don't predict the same energy of the vacuum, and they're both wrong, we're pretty sure. And as per accident, vacuum seems to contain a lot of expansion energy, which seems to come out of nowhere and is driving galaxies apart. So very suggestive that these two things have the same origin. It's some fundamental misunderstanding of how the vacuum behaves, because GR can't do it alone, particle physics can't do it alone, and dark energy is a problem for both. But we don't have an answer yet. But yeah, they're probably related.
Well, we know that that the universe is expanding, right?
Yeah.
We know that everything expands. Space itself is expanding. So we know that this vacuum is, if you take a block of vacuum, it will expand. So there must be some sort of...
Well, not in all interpretations, right? So dark energy, in Einstein's sense, the version he preferred is just that gravity becomes repulsive for things that are very, very far away from each other. So things that are close attract. If they're closer, they attract more. But if they're very, very far away, past the point, they start repelling each other. And that's just how gravity works. It's just a fundamental rule. That's how Einstein liked it. So he added this cosmological constant to make things repel each other if they're sufficiently far away. And that's nothing to do with the vacuum. It's just a hotfix to explain why it happens. But it works too. It's just, could it be something about the vacuum? Probably. We don't know.
Basically, the more vacuum there is in between two objects, the more vacuum pushes those two objects away from each other.
Yes, but we have no idea why.
So it's not like the two objects themselves repel each other, it's what's in between them.
Well, we don't know.
But
what I'm saying.
Just to picture it, the idea.
Yeah, is that the vacuum is pushing on them. The vacuum is expanding very, very slowly, but if you have a lot of it, you'll start to notice.
Well, that means that the vacuum itself needs to have energy and mass.
And the vacuum has energy and mass. That is a thing.
It's a bit counterintuitive. If you think of vacuum, you think of nothing being there, yet there must be something in this case.
Yeah, that's been a big thing in modern physics, understanding that vacuums can have energy and what is a vacuum. And those are particle physics concepts, really.
Yeah.
The idea of pseudo vacuums that aren't completely stable because there could be more vacuum, that kind of stuff. That is a very common idea in theoretical physics.
Okay.
But it's too hard for me.
Don't say that. Don't say that. Nothing is too hard for you.
That's the edge. That's the edge of what I know. Particle physics is hard. Quantum field theory is super hard. Like, what? No one understands QFT.
Well, I hope someone does, otherwise we're fucked.
Yeah, but I don't. I draw the line. I don't understand quantum field theory.
Well, you should study up for it, because we're going to have a segment for it, and you're going to get a PhD just for us.
No. Oh, I know exactly who to sell you for QFT. Oh, I know a guy.
You know a lot of guys, apparently.
I know a lot of guys, because everyone's a guy where I work. I
think
don't want to bother you, but...
quantum field theory is easier, but putting it into words is the hard part.
No, quantum field theory is a mess even mathematically. And GR I can work out. If I sit down and I work out what would be the attraction between these planets and what if it's rotating, you can work it out. I can do the maths, even if I don't have an instinct for it. Quantum field theory, I have no instinct and I cannot do the maths. It's just a mess. It's integrals and integrals, renormalization tricks. It's absolutely terrible. Incredibly complicated stuff to work out.
Okay. Well, I'm sure that someone out there will crack it open, and hopefully it will be correct.
But it works, But...
this makes me think. Maybe we'll do a segment about fields. What do you think?
No. Fields?
Yeah.
No, I don't do quantum field theory. I just said...
No, not quantum field theory, but I don't know, like...
cornfields.
No, that's not...
Well, I mean, I'm Scottish, and obviously, as you know, we have Highland cows. I can give you quite a lot of information on those fields.
No, guys, I mean stuff like, the Higgs field, stuff like that.
No, that's QFT.
Really?
I draw the line. Particle physics and QFT are not what I do.
Fine. Okay, well, let's continue with quantum
I think
then.
even Richard Feynman said no one understood it. And then he understood everything.
That's not very optimistic, is it? I mean,
It's you know, it's like this whole business of quantum mechanics and Schrödinger's cat and wave function collapse and all that crap. It's really about what you expect out of physics. I think there's a bigger philosophical question here. What do you expect physics to be? Is physics just a bunch of rules that you apply and they always predict the future? Because if that's all you want, quantum field theory does it. The Copenhagen interpretation of quantum mechanics does that for quantum mechanics.
aha, we're going to
It
get to
works.
that and why you don't like it.
Well, it works. But if that's all you want out of physics, if you just want a set of rules that always predict the future correctly, but that's not what people want in general. They want understanding. They want to know what it means. We want to think about GR and not only know that we can predict how the planets move, but understand that it's space-time and how it bends and all these cool gravitational effects. We're not happy with just a set of mechanical rules. And unfortunately, some parts of quantum physics can feel a bit like that. Like they are so complicated that the maths almost makes no sense. It doesn't have a meaning. It just kind of works, and we don't really know why. That's how I see quantum field theory, anyway, and the Copenhagen interpretation, which fortunately is finally falling out of favor.
I mean, correct me if I'm wrong, but that is basically what science is doing at this point, is just pushing back the boundary of what we can attribute a meaning to and what not. Because, for example, if ages ago we our ancestors saw a lightning bolt, they knew what the lightning bolt did to the tree. It just put the tree on fire, killed people, stuff like that. So they could know the effect, and they could in their mind think of a rule again, like if the lightning strikes hits a tree, the tree explodes. Fair, okay?
Sure.
But they couldn't really know why it was happening. What is the reason of it? Why is this lightning bolt striking that tree and not that other one? Or why it isn't even a thing? Some people invented gods, stuff like that, to explain it. But then science arrived and said, oh, hey, we can describe it. And then we discovered how lightning bolts happen in nature. But as you push and push, now we are at the point of quantum field theory where we can predict, as you say, but we reached a point where we can't go further. We can't explain the lightning bolt anymore.
Well,
right?
We can explain all its properties that are observable.
Yeah, we can explain the tree exploding.
I think the problem is more that the universe has no obligation to make sense to us. Now, we're lucky that GR is even comprehensible at all. It's so different from what we experience in our everyday lives. It's good that some people can even make sense of it at all. Same with quantum mechanics. Some people can make sense of it. But what if the true nature of physics is something that we can't even comprehend? It will work on paper. It will always give the right answer. But we won't really know what it means.
No, that is a possibility.
What does it mean to have a meaning? I don't know. It's philosophy. Then.
Our brain may be too limited to get this meaning. And this is what I'm saying, actually. We are pushing and pushing and pushing, and we may reach a hard limit where we can say, okay, this may make sense to someone better than us. But at this point, we have a bunch of numbers and stuff that make sense on a mathematical level, but we can't really go further than that. Do you think that will happen?
Maybe. I don't think we're there yet. I mean, you say science, but it's not science. It's specifically particle physics.
Yeah. Well, of course, I'm using generic terms, but you get what I mean.
I don't know. Certainly in cosmology, when we observe a new thing, we also want to know why. Well, cosmology is definitely not at that point yet. But will the theory of everything make intuitive sense? I don't know. Maybe not. It's a difficult philosophical question, and we've really veered away from quantum mechanics now.
Sorry, that always happens.
Philosophy.
It's all cool. I hope our listeners are still being entertained despite us sometimes going off topic. But going back to that, since you like it so much.
Oh, God. Oh, no.
No,
I can see where we're going.
No, you don't see where we're going.
I can see where you're going, Marco.
Where am I going?
We're going to the Copenhagen interpretation.
Yes, right.
I've doomed myself.
Well, not only that, because I mean, we didn't get a question for that, but I believe it is crucial, because when this concept of quantum started getting, consensus, of course there were different theories that happened, of different parts of physics trying to explain why and how to interpret the results. And there is, I think, the Copenhagen interpretation is one of the most famous ones, but it is not the only one. And from what I hear, there is it is not the preferred one.
It
Nowadays.
It depends by who. Well, okay, I don't want to spend more time on this than I have to. I'll summarize it in 5 minutes tops.
No. I mean, what I wanted
it's
to.
a fight starter, even among physicists.
Yeah. Well,
don't mention the general public. Like half of the viewers will want to burn me alive, no matter what side I pick.
I like trolling.
Okay, I'll.
But no, apart from
I can be brutally honest about what I think of the Copenhagen interpretation.
The thing is, we need to start from, an overview of the different interpretations. Then we can delve deep into one of them, but briefly, what are the main interpretations of quantum physics?
Why are there more than one? That's the core of this problem. When people develop quantum mechanics, you had a whole bunch of people. You had Einstein there, Schrödinger, I think a bit later. You had de Broglie, and they all basically came to the same mathematical conclusions using their models. When they noticed that these quantum things were happening, passing electron to slits, and they ended up in specific places, or combining rays of light and getting strange patterns out of it. They all agreed on what the maths had to be. They all agreed that if you had a particle of this mass and the slit was this big and this far away, you have to multiply these things twice and divide by the last one. They all agreed on the maths. But they didn't agree on what it meant. And that's really, I think never have physicists disagreed more vehemently about what was basically philosophy. They could predict what will happen, but what did it really mean? And it got so heated with some people disliking the interpretation that some people were coming up with. A lot of things that were being come up with in the early days about what it meant. You had the pilot wave theory, you had the start of many worlds, you had the mechanical interpretation, all these different things about what it meant. When you observe something, is it literally picking a side because you observe it? Is it because of the observer? Or is it because it's splitting? Or is it because it's decohering? Or is it because there's a secret pilot wave guiding it and you don't know, but actually it's already picked before you see it? People were coming up with all these interpretations, and it got so heated that they all had to get together and yell at each other for a week in Copenhagen, and then they all agreed to disagree. And they decided, okay then, since no one can agree, there is no interpretation. The Copenhagen interpretation is no interpretation. It's saying, shut up, just work out the maths. The Copenhagen interpretation says, sure, it doesn't exist until you measure it. Your math doesn't mean anything until you actually measure it. Everything that you want to interpret about it before it's actually done has no meaning at all. Just forget about it. Do the maths, predict the thing, measure the thing. And that was great, because now everyone agreed, and quantum mechanics was unified, and they were all happy. And it stayed popular for a long time because people don't like thinking about what it means beyond the maths. It stops being really science in a way. If you have the same prediction, who's to say who's right? Is the cat alive or dead or both? Is the wave function collapsed or not? It's a matter of philosophical disagreement in a way. But
you're saying in practice, it doesn't matter.
In practice, it makes no difference at all. The maths was always the same. And then Paul Dirac came along and he made it all pretty, beautiful maths, very elegant, easy to understand. And it worked beautifully. And they had this beautiful thing called quantum mechanics. But don't stop to think about what it means. Just work out the maths. And that's the Copenhagen interpretation. It's fallen out of fashion because we've gone so much beyond that by now. So concepts like wave function collapse say that the place doesn't exist until you see it, or If you don't observe two electrons, one in this room and one in the next room, there's always a chance that they've exchanged places and teleported, but you can't know. And those kind of concepts in the Copenhagen interpretation that you just have to agree that's how the maths works. They've really fallen out of fashion a bit when we started actually digging into those scales with technology and seeing that these things don't really work that way. Particles do seem to have a sort of position. It's not completely unknown. If you trap a molecule in an electron trap for a microscope, like we have now for chemistry, and you keep observing it, it's not going to teleport and switch places to another one. You can keep looking at it. It's there. It has a position. And then quantum mechanics got integrated into quantum field theory, and we had extra concepts on top of it, like the concept of path integrals. Now we have to account for all the possible paths that a particle can have to know what the result of the maths is. But of course, if you just shut up and calculate, the particle doesn't have a position at all. So it doesn't have a path. Until you observe it, it has nothing. Because that's what they agreed on at the time. Nothing exists until you measure it and you calculate it.
Okay.
So these new advances have kind of really started to push the tide. It's happening way too slowly. I think people were very attached to it for a long time. But there's one or two alternative interpretations that are a lot more popular now, I think, with the new generations. Because we're starting to use these things so much in things like quantum computers that concepts like decoherence, when things happen to the particle, even when you're not looking at it, it has a state. They've become much more commonplace. And that wave function collapse isn't some fundamental property of nature, that information doesn't exist until you look at it. It's really what's happening because it's interacting with its environment and becoming dirty, which is an actual problem for quantum computers. It's something we have to solve with technology now. We're not an abstract concept anymore. So we've moved away. Good riddance.
So the Copenhagen interpretation, or lack thereof, was just some sort of placeholder for an actual true interpretation.
Maybe that's how some of them saw it, but that's not what the next generation saw. It was a unifying framework that everyone agreed on. Maybe at the start, some of them were still holding hope for their own interpretation. Bohm really liked the pilot wave interpretation. That one's died too. But I'm sure he was secretly holding hope. It was a placeholder, and everyone would see the truth one day. But because everyone felt that way, they had to just say, those are the rules, they work, don't question it. Things are in a superposition of state until an observer looks at it, and then it picks, period.
Isn't it a bit bad, though, for scientists to say, don't question it? Because that's the whole point of science.
No, I mean, is it? That's the philosophy you were just mentioning.
No,
if all you want is something that works, then that's physics.
Yeah,
that's
but
it.
if you hadn't, we wouldn't have those new interpretations. We wouldn't have to deal to have quantum computing. If we stopped there, we would say, okay, this is how it is. There is nothing beyond that. That's just stagnation.
No, we'd still have them, because to build a quantum computer, you just need the maths. You need to know how your qubits will behave when you combine them in a way. That's fine, that the maths still work, but the concepts start to not really make intuitive sense anymore. And intuitive sense is really all that it's about, this disagreement. And some weird interpretations have maybe extra predictions, like the pilot wave theory says you should see the wave function collapse in slow-mo if you can look carefully enough. Those kind of weird things, but mostly they're exactly the same, indistinguishable.
Yeah, I think that getting deep into the actual individual interpretations will take more time than we actually have tonight. But if there is enough interest for that, maybe we can schedule another segment for that. But yeah, I guess that now everyone has a clearer idea about what the Copenhagen non-interpretation is.
I stand by that. Some people will burn me for that.
I'm going to be very anal, and I'm going to call it a non-interpretation from now on.
It's the mechanical interpretation. And it's really to do with what you expect out of physics.
Okay.
Everything.
But, I
expect everything.
I expect physics to make sense. Maybe it's naive.
You said the universe doesn't have to make sense.
Yeah, but I want it to.
Yeah.
Yeah, that's the challenge. Well, even if there isn't a sense you can make of it, you still have to look for it. Just yeah, well, I do too. So just because it's fun and
Yeah.
enjoyable if you get answers, even if you don't get all of them.
Well,
And because it's easier for people to believe it too, I guess.
well, as long as we don't fall into the trap of, saying, "Oh, there is no explanation, there is no purpose, this makes no sense," and then let's just make up one. That's a bit dangerous. We need to learn to accept. Yeah, I think that we need to learn to accept that some things are just there because of reasons that may not necessarily be understandable to humans as a species. I mean, there's many things on this universe that cats don't understand, obviously. So why do we think that we are supposed to understand everything? That's just naive. We have examples of other life forms that obviously don't understand everything.
But you have to always assume you can, otherwise you wouldn't be trying, right?
Of course, we have to try, but we can't take it for granted. That's what I'm saying.
Yep.
I think we need to keep both options on the table, but thankfully we have people like you who keep trying, and maybe eventually we will learn about how this universe works. Let's see if we have any more questions. We're running out of time,
There's
actually.
plenty.
I'm sure that Michael is collapsing in his cockpit.
Wait, no. I'm just listening to you guys.
You always get tired at this hour.
No, I'm pretty awake. No worries.
Okay.
I'm all ears and I'm enjoying.
Well, I am not, so I don't have.
Oh.
We don't have much time, but no. Okay, let's see what else we have. Are you getting any other questions on Twitch? No.
I see plenty of questions in Discord.
I'm going to go get some pineapple juice, and if you guys don't have a question by the time I get back,
there was one question on YouTube. How do magnetic fields capture iron particles? But that isn't actually a question. I think it's related to quantum physics. Is it?
That's a bit random, but
it is. I mean, electromagnetism has been unified with quantum mechanics into QFT. They've all been bundled up. But,
and you don't want to speak about that?
No, it's okay. EM is okay, but
okay.
That's. I mean, there's no short answer to that.
How do magnetic fields capture iron particles? I don't know actually. Well, I can't.
Is this going to take an hour to answer?
I know. Probably.
I think they just get entrained because they have a magnetic dipole. They just get close enough to be trapped. Iron particles have a magnetic dipole, don't they? I'm not sure actually.
Don't ask me.
I don't know.
I can look up a video
most particles
and share
get
it
trapped.
on the chat if you guys want. I can share a video. Just tell me on YouTube or Twitch if you want to see it.
That's a bit specific.
I'll share that later
you have to
after
look
the
at
interview.
it. Most particles can be trapped by magnetic fields if they're stripped of electrons enough anyway.
Okay. We have
iron core, electrons around it. If any of them are missing, then if you put a magnetic field on it, they will prefer some spots. As soon as electrons prefer some spots, the particles start to have a plus and a minus, and the plus and a minus line up with the magnetic field, and they have to follow the field lines of whatever object is forcing them to move. There we go.
Cool.
That's the short and easy explanation.
We have a question from earlier. About 1 hour and 15 minutes ago. I hope that Morris is still with us. And he asked what would happen if oxygen met antimatter in the form of helium. What would the resultant atom be after the energy discharge?
Depends on the conditions of their encounter. Most likely some sort of radioactive material, unless you really control your environment. So you interact your oxygen with helium, the first thing that will happen is...
No, he says oxygen met antimatter in the form of helium.
Antimatter in the form of helium. So you have an antihelium. It contains positrons, presumably, as well as anti-protons in the forms of opposite quarks. Well, if they touch each other, immediately the energy from the explosion will blow away the rest of the atoms anyway. So you'll have no oxygen or helium left. You'll just have a bunch of particles scattered around until they all lead to small explosions. And depending on what they collide with, you're going to have various radiation leftover materials, depending on how clean your explosion is. If it was in a vacuum, you can probably work it out what atoms they would prefer to end up as.
Wouldn't an explosion of such relatively high mass elements like blow up a very, very large area?
Yeah, it would.
Mm-hmm.
Sure. And how much energy is in a proton? E equals mc squared, mass of a proton.
Mass of a proton.
Can we make bombs out of this?
Well, yeah, antimatter bombs. That's the thing in every sci-fi ever.
Yeah, I mean in reality.
Well, no, we can't do them in reality yet. In the Da Vinci Code.
Say yet.
Well, yet, of course, yet. You just have to find a way to preserve your antimatter. That's what we can't do yet.
American military, get on that.
Yeah.
They're on that, I bet you.
Probably.
I'm sure they're on it, but I'm not even sure it would be efficient. I mean, it would be so hard to confine it, to stop it from exploding immediately. You'd waste so much energy just trying to keep it from exploding. You might as well, just have more nukes.
Yeah, I guess.
I think.
Yeah, I guess it's not exactly cost efficient, but... Well, okay. I hope that Maurice heard that answer. We have other questions which are not really quantum related, so...
I saw one about neutron stars.
Yeah, exactly. They're not exactly quantum related.
I think...
You want to talk about it? Sorry?
I think I'm not sure if I've seen the same question, but I think the specific question was actually about the relationship between neutron stars and quark stars.
Oh.
Or have I seen a different question?
I may have missed it. Wait.
Or have I made that up because I like that topic?
You mean the one from Kvanti?
I think so. I'm just looking for it here as well.
Yeah, Commander Kvanti asked this question. It would be interesting if you could talk about our current understanding of what's going on in neutron star cores, like the nature of quark, gluon, plasma, and how it relates to strange stars. I'm not sure what strange stars are.
I think strange stars is in reference to strange quarks, because I think the idea behind it is that, I'm not entirely sure of the exact things, but there's a certain amount of energy where it's not collapsing into a black hole, but it's also not. It's such a high energy that it's not a neutron star because it doesn't stay as neutrons.
Yeah.
I think that's what they're talking about.
Oh, seriously,
yeah,
sorry.
that's...
I was scanning a planet. Sorry.
Yeah, that is something I've heard of before. The neutron stars, basically, it all comes down to how much can you squish matter together. How small can you make something? If you compress it and you keep compressing it under its own mass. Of course, we all know the most massive thing you can ever have is a black hole. But before you get to that stage, now how much can you break down matter by trying to press it together? So you have all these stages of things that would stop collapse. So stars can support their own mass because they're so hot, and heat generates convection flows, and heat just tends to give random motion to particles. So they push back using their heat and nuclear reactions. But if you get too heavy, you can't do that. That's not enough anymore. So you collapse to a white dwarf first, and then to a neutron star, and that's just different stages of other things that can keep you from collapsing further, kind of like steps that you can hang on to on an infinite fall to becoming a black hole, like things you can grab onto. So if you reach the stage of a white dwarf, you're basically supported by electron degeneracy pressure. Your electrons don't want to be on top of each other. In quantum mechanics, we have this rule that particles can never be in exactly the same state, or at least fermions can't. So if you get all the fermions in your star and you try to push them together, they will not want to be on top of each other. They cannot be. So that's going to hold you up for a while. If you become even more heavy, even that's going to fail. The electrons are just going to basically decay into energy and fuck off. So they won't help you anymore. And you're left with more and more exotic things that can keep you from collapsing further. So you reach neutrons, which give you neutron stars, where only neutrons tightly packed in the center don't want to be on top of each other. So they're repelling each other slightly just to stop the collapse as much as they can.
Are you talking about neutron degeneracy?
At that point, yeah.
Yeah.
You reach a type of neutron degeneracy, which is really a strong false argument. So your neutrons are made up of up quarks and down quarks, normal quarks, bundled up together in blocks of 3. And these groups of 3 don't want to be on top of each other. It's kind of the same. They can't occupy the same physical space. Some other particles can in quantum mechanics. It's called the Bose-Einstein condensate. It's a different type. But those neutrons can't do that. So they become squish, can't go any further. And that's really what a traditional view of neutral stars kind of stops. You can simulate what happens to particles on that stage. You have lots of different layers that you get from this pure neutron matter. They have a crust that can have star quakes. It's got quite a crusty crust on the outside, and different types of basically neutron crystals all the way to the core. More and more tightly packed, basically. So you get like a neutron crystal with many layers. But then we have this theory that actually if you keep pressing them further, well, we used to think there was nothing else. After that, if you're too heavy even for that to keep you just become a black hole. But now we think there might exist a more efficient way to combine these quarks together to save space. And that's by turning them into strange quarks, or basically one of the two cousin variants of quarks. So you have your up and your down quarks. First off, they can try to lose their structure and not be in groups of 3 anymore. That's one way you could maybe get them even more closely together. Then it's just quarks at the center, not neutrons anymore. And then more than that is when you get to strange stars and strange quarks, because maybe those could give you a more efficient packing. If they're forced to transform into those other things by pressure, they will do it because it's the only way to still resist the collapse.
We haven't seen anything like that.
Well, we've seen neutron star crusts. They're very well studied. These are neutron star crystal earthquakes. Very common observations, and they work very well. So we know that the outer layers are definitely correct. That's not the problem. That's fine. It's just the cause. Like, what states of matter exist is the fundamental question. No way we could ever do it on Earth. No way.
I was going to ask that, but I guess, yeah.
Yeah, no, I mean, this amount of compression, there is no machine on Earth that can replicate that. No way. It's pressures that we can barely imagine that this matter is being forced into, that even atoms and fundamental particles just give up being what they are. They give up being neutrons just to be able to be packed together. And it's all the laws of physics give up at some point.
Well, but I mean, you said that if you press matter together, it becomes energy, right? Like electrons. That is something that we do with explosives, no? I mean, with...
yeah, maybe I didn't express myself well. So when
I'll probably just dump myself when I don't understand. But...
No, you're right. The point, that's how explosions work. You take some mass and you transform a bit of it into energy, like E equals mc squared, Einstein's equation. You take all the stuff before the bomb goes off and all the stuff after, and some mass has disappeared. Where is it gone? It's become energy. It's the explosion. That's not really what I meant by electrons give up. I mean, they physically leave. So they're being packed together in this collapse. Then they say, oh, I can't go that way because there's other electrons there. I can't go on top of them. And they don't have a choice but to go the other way, even if it involves in some cases flipping their polarity, becoming positrons because they're forced to. They have no choice.
Yeah, but they emit energy doing this, right? Or not?
Yeah, I mean, they do, but they also leave. So the star loses both mass and energy. That's why supernovae are so violent, because all this energy is going away, in a way. At least part of it.
Okay.
Mhm.
Okay, so quark stars.
Yeah, so quark stars. They
We don't
may
see
exist.
them. We don't see them as we are exploring the galaxy here on our way to Beagle Point. I guess that our sensors are not accurate enough to detect them. We go directly from neutron stars to black holes.
Well, I'm not even sure you could tell the difference. It might just be inside the deep reaches of the core that these types of matter exist.
Hmm.
The neutrons on the surface wouldn't mind living there. The ones at the center would give up.
I wonder if there will be a way to actually detect this difference. Seems quite hard to do, even with the. I mean, you have to poke inside a neutron star. I'm not sure how you would be able to do that.
Well, we can, thanks to LIGO.
Oh, okay. You have to wait for
For
them.
the commercial break, LIGO can
No,
make us
we-
see inside neutron stars.
We're a bit late for the commercial break, but sure. I know that LIGO detects, merges, but we need to wait for them to merge.
Yeah, sure. But by the way they merge, we can make out what their density is at the core. And if really there is something that can exist that is more dense than even pure neutrons, then we could see that their cores are more dense than they should be. That would give us a big hint. Once it becomes precise enough, thanks to the successor of LIGO. And
There is a successor planned.
I'm having a blank. God damn.
It's getting late.
Someone on the Discord
You can
will
use
find
Google.
it for me.
You can just look it up.
No, that's cheating. No, you can't use Google. That's
Google.
no,
Aw,
you can't.
come
It's
on.
cheating.
If you
No,
can't use
can't.
Google, use Firefox.
That's what?
Chromium.
That sentence doesn't make sense.
It's
Well,
Lisa.
it did for Chrome users.
I knew it was Lisa. Should have known that. Yeah.
No, Google is a search engine, and Firefox is a browser. Okay,
Oh,
it's
it's
two different things.
right.
Also the
Right.
It doesn't compute. Okay.
You
does
see,
not
I'm
compute. Computer says no.
Anyway,
Nowadays are basically the same. So it's Lisa. Lisa is a successor of LIGO. It will be in space.
it's LISA then.
Lisa. Laser interferometer. LE. Lisa.
Okay, because LIGO is already outdated, I guess.
Well, Lisa will not launch until 2030s and a bit.
I heard
They're
about
doing-
this.
They're doing the test run now. They have a small scale Lisa that's going up in space to check that it works in space. But the big one will be the 2030s. And
Aren't they
mostly
using
European.
Aren't they using the test one to measure the density of different parts of the Earth, like with the differences in the, like I think, or at least the satellite I'm thinking of, it essentially with the increased density of different parts of the Earth, that will increase the required orbital speed, and therefore one of the satellites will go slightly forward relative to the other one, and then that will catch up. Is that the
That's one of the
test, or
things-
is that something else I'm thinking of?
That's one of the things we have to worry about for Lisa, actually, because so Lisa will bounce this laser instead of using a vacuum tube like LIGO does. It will just use space because space is already a vacuum, so that's easier to build. But you have to know exactly how far away your partner satellite is if you're going to bounce a laser to it and it has to come back. So you have to know exactly how you're going to naturally move due to the gravity of the Earth, and that's going to be influenced by which parts of the Earth are heavier, like things like mountains and stuff. So we have to test that to know exactly what the normal path is so that we can see variations from the path. That is one thing that they're preparing for.
Okay.
Then
Well, there is
complicated at that.
there is Ganlan who was listening in despite not being in voice comms anymore. And as you were talking earlier about the strange stars, he's asking, what about magnetars? I'm not sure what the context of that question was.
Compositions of stars, right?
Yeah,
Well,
it's not the first
we
time
were
I
on
see
the topic
someone
of neutron
mentioning.
stars.
Excuse me?
We were on the topic of neutron stars, and I believe that's
Yeah.
connected
Yeah,
to
yeah,
black
yeah.
stars.
I mean, by this point, as usual, we were supposed to talk about a topic. We're digressing as usual. But it's fine. It's getting late.
Are digressing.
Yeah,
But still.
magnetars. I don't know. As far as I'm aware, they're the same, except they have stronger magnetic fields. So it turns out if you start with a star like the sun that has a magnetic field, it's quite weak compared to how big it is. But as it collapses until only the core is left, the magnetic fields kind of become embedded and they don't get lost. So as a proportion of the size, something very small as the remnant of a star has a star scale magnetic field, even though it's super small. So it's extremely magnetized. They all usually are, but magnetars are like the most magnetized neutron stars out there. They've kept in their crystal structure the alignment of those fields. And there's a bunch of theories as to what that would do to the structure. I think it makes more efficient jets. Is the most commonly agreed one. Same as black holes, really. If something is very magnetized and stuff falls onto it, it's going to be jetted out at higher speeds. But yeah, magnetic fields are a bit hard to measure unless you see it interact with stuff.
Okay. Well, we have just a couple of questions left. One from Olmi. I believe it was answered already by Selfish Pie, actually, by a text. I read it briefly. I believe it is correct, but I'm not an expert. He was asking, because we were talking about observing things, quantum particles, electrons, and observations make things collapse. And he was asking, is there anything else apart from human observation that can collapse a particle? But of course, everything counts. Everything that interferes with a particle is considered an observation. It doesn't have to be a human eye.
It depends on your interpretation. In practice, it looks like things decohere with anything as long as it's complex enough. Definitely being seen by a human is more than enough. I mean, if you see the outcome of something, then that outcome state is interacting with all the parts of your brain. So it's interacted with so much stuff at that point.
But not only that,
definitely collapsed.
Even if you use like a sensor, polarized sensor, that we humans can somehow translate to information, even if we can't directly see it with our eyes.
Yeah,
it is still more than enough.
Yeah, I've had this debate with physicists before. If an observer sees it, or if a rock sees it, is it the same? Kinda.
That's why I think observation is just a bad choice of words for it. I think interaction would be the better term to talk about it, because interaction just is
observation is a bit. Well, observation in physics doesn't have the same meaning, does it? Observation just means measurement in physics, but people don't use it that way in everyday speech.
Yeah, that's where.
Yeah, so there's a bit of
and then there
misconception about that.
Fringe interpretations that say it's really when it's perceived by a consciousness that it collapses. And people who shouldn't be saying such
bullshit. If a tree falls in the forest and no one's around to hear it, does it make a sound?
Yes, it does. It moves the air.
But no one is around to hear it.
There has been a study done where...
How can you prove it made a sound?
There has been people who have looked at a crisp packet on the ground and have used incredibly sensitive lasers to measure the small dentations in the crisp packet and they've been able to decode those indentations to hear a conversation in another room around a corner. So I think if we had...
But you observed it with lasers.
No, we didn't observe the conversation. We observed a crisp packet that was closer to us with those vibrations using lasers. But it wasn't that...
The crisp packets observe the conversation. And then you observe the crisp packets.
Fair enough. Jeez.
Yeah.
Fine.
Aha! I broke
Fine.
the
The air in the room of the other room is observing the conversation.
Exactly.
Carrying the
Exactly.
sound waves through the wall to the crisp packet, and so on. But
And the
interaction
camera
with
is pointed at the
things.
crisp packet.
Since
that's
everything
recording
is
it,
connected.
Right, okay, I get the point.
Everything-
It doesn't work.
It's cool though.
I disproved
But
that
it works.
experiment. I will write a
No,
paper
it
about
did
it.
work. They did manage to reconstruct sound, which is really fucking cool.
Yeah, but it
Yeah.
doesn't really
But-
prove what I'm saying.
No, it doesn't.
It wasn't very high
Nothing to do
quality,
with
but you
quantum
can hear
mechanics,
words.
but
It was
it's
really
cool.
cool.
Still, the tree may not make a sound if no one is around to hear it.
Well, define sound.
Sound
Define
waves.
your level of proof. Physics
Let-
isn't philosophy.
Next question. We have actually, I don't know, I may have missed something, but it's getting late. So, okay, last question. I'll give you a choice between two.
Okay.
One is from Shaggy Dog. How many cats would accumulate enough gravity to collapse into a Qtron star? Before answering, that is the first question. Okay. Second question is: can you explain Hardy's paradox? Now, which one of these two would you like to answer?
Oh, jeez.
And which one do you think has an easier answer?
The first one. That's easy to answer. I can work it out on my
We want
calculator.
an
Give me a
Accurate
second.
number, yeah.
Really?
Yeah. I'm going to calculate the number of cats it would take.
Yeah, but cats
Okay.
can have different mass depending on how old.
Average. At that point, it won't matter. Average cat mass.
Yeah, but you need
What's
to
the
collapse
Google
average
into.
mass of a
skills,
cat
okay?
with standard deviations included
No,
for the uncertainty?
wait.
4.
For what?
Okay, so
No, but
1.44.
You didn't read the
solar
question
masses
correctly.
Divided by
you didn't read the
a
question.
neutron star.
Yeah, exactly. What is
Yeah.
a Qtron star? You need to define that.
It's made of cute neutrons.
She's actually
For
doing
anyone
it.
who wants to know,
She's-
I'm just gonna quickly tell what Hardy's paradox is.
Sure, I mean, she's literally calculating things now, so in the meantime, you can introduce the paradox. But it's going to be quick because we are reaching the 2 hours mark.
Yeah. Hardy's paradox is a thought experiment in quantum mechanics, of course, which in which a particle and its antiparticle may interact with each other without annihilating. That's Hardy's paradox. Well, the gist of it.
Yeah, when kind of. Yeah, okay.
Yeah, I'm just pulling it straight from Wikipedia
Oh, okay.
because
I mean, it doesn't tell
I-
you like what it means. Well, wait.
yeah,
give
I
me
saw it on
one-
PBS Spacetime.
Yeah, no, she's still busy calculating the cats.
I don't know what the number
Yeah.
is called. Okay, so it's a 1 followed by 7 followed by 29 zeros. That's the number.
29 zeros.
Yeah.
Yeah, well, 7 times
3,000.
10 to the
6 is million. 9 is billion. 12 is trillion. 15 is quadrillion. 15, 16, 17. 18 is quintillion. 19, 20,
21 is.
It's
You
a
can-
lot, right?
Sex-
You can type it. You can type it in the chat so that
So-
people
Hang
know
on, yeah.
what Qtron
14,
star
15.
would be.
It's 0.7 peta cats. Okay. It's a lot of cats. It's a 1 followed by 7 followed by 29 zeros.
Peta cats.
Peta cats.
That would be,
0.7 peta cats.
Extra,
That is going to be my-
kilo
that's
extra
going to
cat.
That's going to be my next ship name.
No,
Peta
not
I think it's a
that.
tera exa. I think it's a tera exa
Yeah,
cat.
Terrax.
Terra-
0.7 tera exa cat.
sounds way cooler. Terra extra cat.
Yeah, that is actually cool.
Jesus. Okay, Hardy's paradox. Hardy's paradox really is about hidden information. So, based on the experiments that we can make, including versions of Hardy's paradox, is it possible that the information about what spin a particle is really there, but it's hidden? So it's there, it's already picked plus or minus, but you just don't know it yet because you're ignorant. So it's really about what information is present. And what Hardy's paradox shows by conducting this thought experiment and physical, it had been tested in practice but not very well, is that you can have you can have hidden variable theories only as long as they're not local. So if I unpack that, if there is hidden information, then it has to be influenced by something outside of your control. Or if I rephrase it again, local means events can only be caused by things in their immediate vicinity. They always have a deterministic reason based on local effects. Well, Hardy's paradox shows you can't keep that locality property if you want the information to be there and hidden. But there's a few asterisks next to it. It's a bit more complicated.
Yeah.
As with
But basically,
everything.
he was trying to disprove hidden information theories or hidden variable theories, as we call them. That the information is not there. It's really, it really appears during the process of decoherence / observation / collapse. It's not always there. If it was, then Hardy's experiments wouldn't work.
Okay.
Yeah.
Well, Michael, if you want to have more information about this, just talk with her in private, because we're running out of time, and that is true for anyone else. That is true for everyone else who is listening in. I hope that we helped clarifying some of the doubts you have about quantum physics / mechanics and other things. If you still have questions, Shoba is usually willing to answer them privately, time permitting. I know
or
that
just tag me on Discord. I'm usually around in the evenings.
Or that.
Okay.
So feel free.
Will do. So.
Yeah, we still have to pick a topic for next week. We'll think about.
Let's go back to astrophysics.
Yeah, that was the idea, but exactly about what?
Early objects. The first galaxies and the first quasars. Let's go back to what I actually do.
All right.
Can we do that?
That sounds like a plan.
JD something. I saw it on your YouTube channel. The oldest galaxy we discovered yet.
The most distant galaxy ever found. That was in May last year.
Yeah, well, I watched the video, but some of the viewers or listeners probably haven't. And if you could talk about that, I'd be appreciative.
Yeah, let's go back to early galaxies and quasars. The first.
That is your turf.
Yeah.
So we will do that next week. We'll go back to the start of everything and the oldest things in the universe that we can detect. We will do that next week. And remember that there will also be an article on the newsletter this week.
Yeah, I didn't realize the deadline had moved. The newsletter has moved from Sundays to Thursdays or something, so I missed the last one. I'm sorry.
No, there was no newsletter last week.
Ah, okay.
At all.
That explains right.
That explains things.
Yeah.
Well, I'll have one. I have an article this week
because Dr. Kai decided to move the deadline to the following Thursday, so there was no newsletter last weekend. So you didn't miss anything, but you have time until tomorrow.
Yeah.
So will you be able to manage that?
Yeah. I have a cool topic this week.
Oh, I'm looking forward to
it. So make sure to check the newsletter, guys. If you haven't done so, you can read the previous articles as well, together with the previous episodes of Dangerous Cosmology, which have been uploaded. I think this one will be uploaded there, same place, right, Michael?
Yes, and I'm trying to do it as soon as possible. I'm promising that it will be online tomorrow, but at least latest tomorrow evening, but I'll try to be
because I know that
early as possible.
Many people in the US don't have a chance to follow this live, so at least they can listen it after it is done, and if they have additional questions, they can always ping Shoba after they listen to the podcast. So this is it from me, guys. Unless you have some last minute questions, we can just end this segment here. Yes, Michael?
I think so too. I'm
Okay.
getting ready, so let's say goodbye, everyone.
Thank you, guys. Thank you for listening in. Thank you, Selfish Pie, Michael, for being here, Ganlan, if you're still listening. And of course, thank you, everyone who stayed until the very end. I see that there's about 30 people listening in now. I believe that 25 are AFK. But hey, if you're not, great. But hey, that's good.
Well, as long as you keep inviting me back, I'm going to assume someone is liking these
Yes,
shows.
at least me. So, as I'm the boss of the radio, you'll always have a spot here.
Yay.
So thank you, of course, Shoba, for taking time for us. And this has been Dangerous Cosmology, straight from the Red Comet as we fly in the dark. I will see you out there, and of course, next week. Have a good night, everyone.
Good
Yes,
night.
good night,
Bye.
everyone. Thanks for watching and listening and
Bye.
tuning in and everything. And yeah, we will see and hear each other later. Goodbye.
See ya.